This video is about permutations of like objects. Consider Woolloomooloo. Woolloomooloo is a real place. It's a suburb in Sydney. I'm not kidding, look it up. And it's an interesting word. It's got some repeated letters in it, and it's got 13 letters in total. And 4 are different. It's got 4 different letters. So W, O, L, and M. And basically all the O's have little subscripts. There's 8 of them. And the L's have little subscripts. And you can see there's 3 of those there. Now, permutations of like objects are a bit different to just regular factorial type permutations. If these were all different letters, we'd have 13 factorial different permutations. But the thing is, without these little subscripts, which we don't normally have on letters, for identical letters we have fewer actual permutations. So normally switching letters does not make a new permutation, so we need to do something about this, and clearly the number of total permutations in Woolloomooloo is not going to be 13 factorial. So let's have a look at what we need to do. So consider a case where we have the 13 factorial, so something equals 13 factorial. That is to say, if we had the 3 L's were all distinct, if the 8 O's were all distinct, and we factored in all of the other permutations, which I'm going to call P, all of that together would make 13 factorial based on our previous work. However, as we said, we don't have these, so what we need to do is rearrange this, and the number of true permutations with these like objects would be a rearrangement of that 13 factorial over 3 times 8. Each factorial's on the bottom, so 13 factorial over 3 factorial times 8 factorial. In general, when we have permutations of like objects, the number of permutations for n objects has a general formula. So that means for the total number of objects, it's that number factorial over repeating objects. They're the like objects. So if we've got, in this case here, we had type 1, which was the repeating L, type 2, which was the repeating O, and we might have more. They are all multiplied down the bottom up to the last one there. So let's have a look at some examples. Some examples, riffraff. Okay, riffraff is not a nice thing to be called. There's the word spelled out there. We have 8 letters. So by itself it would have 8 factorial permutations. But of course we've got F's repeated, R's repeated, and we need to consider those. And how many R's have we got? We've got 2. And how many of the F's have we got? We've got 4 repeated. So we need to consider those. So using our permutations with like objects formula, which we've established, we can substitute that in there. So we have 8 factorial divided by 2 factorial times 4 factorial. Remember, in a calculator, that's essentially what's happening there. That gets grouped together, and 840 is our answer for that. So there are 840 permutations of riffraff if F and R are not distinct, which in regular usage then they certainly are not distinct. They are all the same. So swapping the F's, swapping the R's and so on does not create a unique or a different permutation necessarily. Final example, down the bottom I've written 4 knives 3 forks, 2 spoons. And that means 4 identical knives, 3 forks and 2 spoons. All of those individual bits of cutlery are basically identical. And so how many different permutations can we come up with? Okay, so we've got 4 and 3 and 2 is 9. So let's have a look. That would be 9 factorial by itself. However, we've also got to consider the 4 identical knives, the 3 identical forks, the 2 identical spoons, and basically we have to divide by those there, and we can use our calculator for that. 1260 is the answer. So there are 1,260 different permutations for that situation.